So today I would like to motivate the course why we need to study machine learning and why it is so much interesting, especially this time around. So everything is starting with the notion of AI, artificial intelligence. So everybody is talking about AI these days. So AI is defined as algorithmic methods and their application to understand, analyze, predict life phenomena represented in data. So where something represented in the form of data and we want to analyze it, and we want to understand that, and we want to make some prediction based on the pattern in the data. And data, again, can be defined as collection of information from the observation in storable format. So where table, spreadsheet, text, image, waveform, whatever. So whatever you have stored in your hard disk drive or solid state disk, they could be understood as data. And there are a big engineering layer to understand and analyze or parse these data into some manageable format. And on top of it, we are building some of the program that can analyze those data and that can capture some patterns from the data, and using the pattern that can make some prediction. So all of these kind of activities can be understood as an effort in AI. But some of the AI methodology, they don't require data. So I'm going to make that distinction in the later slide. But anyhow, this is one of the possible definition of AI. And Ray Kurzweil once gave another definition about AI. So science and engineering of making intelligent machine, especially intelligent computing programs. So there are a lot of intelligence going on in definitions and stuff. Well, anyhow, that is sort of brief definition of AI. Moving on to machine learning. Machine learning is subfield of AI. So AI is the bigger group of concept and bigger group of practice, academic practice. And machine learning studies the design of a computer program. So we are focusing more on the computer program, and that is capable of learning from past experience or adapting changes in the environment. So this is something called as data. And changes in the environment, this is environment. But this vocabulary is used often more in reinforcement learning setting. Well, anyhow, we are focusing on the definition, so let's touch the detailed stuff later in the semester. Well, moving on to second definition that I prepared, this is written by Kevin Murphy, so a set of methods that can automatically detect patterns in data and use those uncovered patterns to predict future data and to perform any kind of decision-making based on the prediction. The definition is more focusing on decision-making and uncertainty. And the third definition, a computer program is said to learn from the experience with respect to some class of task T, and the performance measure P. And in that case, performance is improving with experience. That is the definition of machine learning. So where we are focusing on some kind of a program, computer program, and we have set up data. By providing this data into the program, where this program is able to improve. That is sort of conceptual definition of machine learning. Well, that being said, let's get on the history of machine learning. So the term machine learning was first used by Dr. Arthur Samuel. So he was an engineer and scientist in IBM. And he was also famous with his invention in computer program that is able to play checkers. So checkers is a board game, and you have 15 different pawns, and basically the goal is eliminating all the other four of the opponent. And he wrote his first program that is playing checker on 1952 or something. And later on, he will sort of write textbook chapter related to how to build the game playing program for checker. And this was the book chapter, the first page of the book chapter. And on this book chapter, he used the notion of machine learning for the first time. So given some of the situation, he invented and he presented a way to improve the performance of the program. and that was the beginning of the machine learning, idea of machine learning. So there are some kind of a recurring concept. So machine learning used something called as a model, and also something used something called as an algorithm. And these two play together to progressively improve the performance of some task. In this case, models, mathematical representation of data or decisional behavior, and algorithm that builds a mathematical model using something called edge data or training data. And by using these two components, here comes the eventual goal of machine learning. So we don't want to specifically program something. We don't want to write everything specifically, and we don't want to describe every details of program behavior. But instead, we want to learn something from the data. We want to collect a bunch of different data, and we want to let the program or let the model automatically run those tasks or decision behavior. So where we started our discussion with the definition of AI, and we are narrowing down our scope of discussion to machine learning. And later on in this semester, we will touch the basis of deep learning as well. So there are some algorithms that does not need data at all. So sometimes you can build a intelligent task even without data. Where AI is defining some academic practice, we want to perform some intelligent tasks. So that is the superset of everything. And some of these tasks, they need data. Some of these, they don't need data. For example, if you build some program based on the logic, so there are first order logic. In this case, you have set up a statement, set up a proposition, but you don't need data. And some related topic is constraint satisfaction problem. And also, there is a traditional program called the pathfinding. So given a maze, you want to find a way out. And this is basically such a problem, where all of these programs, the solution to these problems, they are intelligent program, but they don't have to have data. So if you want to find some AI example that is not in the class of machine learning, you can name these. So there are some intelligent tasks, they need data, sometimes they don't need data, sometimes as well. Well, if you want to find AI approaches, they don't need data, these are the examples. Well, machine learning, like we discussed in the previous slide, we still want to build some intelligent program, and they are learning from data, and they are improving based on the data. So the difference between this group and this group. Maybe the quiz question is the solution improving based on the data? Well, anyhow, throughout the semester, we are going to study linear regression, logistic regression, support vector machine, decision tree, Bayesian network, and so on. So all these models or all these solutions are examples of machine learning. And deep learning is a subgroup within the group of machine learning. So again, there are certain solutions called as a neural network. And if you build the architecture deep and big, then that is called as deep learning or deep neural network. So throughout the semester, we will touch the basis of a neural network, deep neural network, convolutional neural network, LSTM or recurrent neural network, and so on. All these are examples of deep learning. So AI is becoming something, and machine learning is the key player in AI. And there are clear background has been set, and that allowed us to have something called as AI explosion finally. So even when I start the study of machine learning and related stuff in graduate school, AI was not one of the major topics in computer science in general, but somehow it has been become something. And there are some of the clear background that allowed where this kind of explosion happened. So one is improvement in data storage. So machine learning that is relying on a large quantity of data, where data storage technology is improving that allowed us to store more data, and more data is eventually sort of bouncing back some of the benefit to us. So that is sort of the logic. And increasing computational resource, where not only the data storage, where we have better CPU and more computational power with the provision of the GPUs. So we will talk about that in the later slide. And also, where we now know how to perform those computational tasks and statistical tasks better. So maturity in those methodology is another background. So let's touch the basis of each of those bullets one by one. So the first bullet, improvement in data storage and processing technology. So mid-50, the hard disk drive first came to the world. Where at that time, well, I don't recall exactly, but where this big stuff over here, it was about 250 megabytes or something. And we knew how to store the data in magnetic format for computers. And later on in 80s, where now we learned how to store data more than 1 gigabyte in hard disk drive. And at the same time, we used a bunch of these magnetic tapes. Well, the point I would like to make here, where about 50 years ago, this is basically tape. So where each of these roll is about 50 meters in terms of length. And in order to load data to the computer, you need to read all of these magnetic signals out. So you need to load it over 50 meters of tape, and that will take a lot of time. So reading data from the storage take hours, and writing back your data to the storage also took on hours. So reading and writing data was not very easy about 50 years ago. But those storage devices are getting better. So floppy disk drive came up to the wall, and these days we are using micro SD cards or USB thumb drive, and even this small box of disk is as much as 20 terabytes or something. So the price for the gigabytes getting lower very fastly, and this allowed us to store a lot of data. So data availability, let us use better algorithm and better experiment, and eventually we have more data. So especially with World Wide Web, so internet, where there are 2 billion or more than 2 billion of web pages and more than 500 hours of content uploaded every minute on YouTube, and genomic signals of thousands of people, they are being created in the labs and so on. So there are a bunch of different data sources, and we are now able to store all of these signals in some format. So where that is big changes, and that is a big background in AI and machine learning. And the second bullet that I would like to mention is improvement in computational resources. So there is something called as Moore's law. So number of transistors on microchip is being doubled every 2 years. So that has been around the 1950s. So this law has been out there for more than 70 years. But still, if you consider the central processing unit or CPUs, where this is sort of low, we're sort of working. So everything is being doubled, where the number of transistors, so number of computational power is being doubled every 2 years. So that's the basic idea. So every 2 years, you have twice as much computational power available with your computer. Well, this is good, but there is something better in terms of that transition. So there is something called the GPU. Initially, this has been out there for computing the graphical stuff. So in graphical stuff, you need to compute a bunch of matrix computation. If you consider matrix computation, each of those operations is very easy, but you need to compute lots of simple things a lot of times. So CPUs, usually Intel CPU like this. Each CPU has a few thousands of instruction in it. Here, instruction is from the computer architecture. So if you want to play video where Intel CPU or some general purpose GPUs, well, that would be your choice. But if you want to perform large scale matrix computation, well, GPU would be better choice. So it has, well, CPUs usually have 2 to 16 cores in it, and it can handle 4 to 32 tasks at the same time. For GPUs, the scale of the computation is different. So one of the latest GPU from NVIDIA, it has about 10,000 cores in it. That means it can handle 10,000 computation at one time. And each of these computation, if you look at the operation, they are much easier compared to what CPU can do. But in machine learning and in many numerical algorithms, where you don't need that kind of complexity for computation, you need simple and very fast and very large scale computation to handle those algorithms and those problems. So where GPUs allow us to do that. So basically all those graphics are representing that. And here comes some quick comparison between CPU and GPU. So where if you are interested in computer architecture, or this kind of discussion should be very interesting as well. So CPU, basically, it has a control unit and it has a bunch of ALU, but this bunch is usually in the range of 2 to 16. And it has a cache memory and it has a DRAM. And GPU has, well, something corresponding to ALU, but the scale is much bigger. So it has at the scale of a few thousands these days, and it is being increased every year. So there is something called as Huang's law. So the CEO of NVIDIA. NVIDIA is one of the biggest company in GPU market. So the performance of GPUs will more than double every 2 years, sort of new law. So here comes the performance improvement in GPU. So as time goes by, GPU is improving, where CPUs are improving at that scale. And this is the graph showing the improvement in GPU. So it is rising much rapidly. So there are some other aspects in these histories, but where I would like to focus on the current point. And within less than 10 years, there are a bunch of different changes, well, quite rapid changes in terms of the technology and also the study of machine learning. And what made this could happen was sort of listed out in the previous slide. Well, one of the last bullet is maturity in computational and statistical methodology. So, well, this is some changes happening at this point. So, number of publication and number of patents in AI and machine learning that is increasing rapidly within last 10 years. And in the field of AI in general, the number of published papers in academia is rapidly increasing as well. And also those scientific and engineering conferences related to AI, it is gaining huge popularity. So it was from 2018, where NIPS is one of the main conferences in machine learning. And usually up to 1,000 people are participating in this single event. And 2018, where that was before the COVID-19, so offline conference was held at the time, and the 8,000 ticket was sold in 12 minutes, something like that. So, well, this sounded like a rock concert, but well, it turned out an academic conference. So all of these were sort of ongoing changes, and also something happened like within 30 years or within 20 years, and all these are allowing us to experience these big changes in machine learning in AI. So improvement in data storage and improvement in computational resources. Well, this is something allow us to do all these, but eventually we want to focus on the improvement in methodologies. So this is our focus. So throughout the semester, where we are going to talk about different methodologies and different algorithms and different models in machine learning. And this is the last topic that I prepared for today. So there are three main types of machine learning, and we are going to study throughout the semester this guy and this guy, and this is not sure. Well, first of all, supervised learning, where supervised setting, you have given data instance number 1, instance number 2, through data instance number n, and each data instance comes in pair. So x is usually referred to as the input vector, and y is desired output or target. So given these pairs of data, x and y, you want to find a mapping f. So from x, you want to go to y. That means f is a function, and if you put x in this function f, you will get something similar to y. So within this kind of mathematical notation, you have two representative problems. One is regression. So x is discrete or continuous, and y is continuous. So your target is important. So based on where someone's health profile, you want to predict life expectancy. So that could be one example. Another representative problems in supervised learning is classification. So x is again discrete or continuous, and y is discrete. So the difference is here. So based on, again, some health profile, you want to predict if this guy has a disease or not. That could be an example of classification. Graphically, we can give some notion for regression and classification in this way. So based on the input value, you want to predict life expectancy. That turns into a line that crosses in the middle of your data. So based on the observation related to each person's health profile, you want to go to the y-axis, that is life expectancy, and you can draw a line, or a predictable line like this. Well, here comes the case of classification on the other hand. So based on some genetic information or health information of each person, so you can plot each person's genetic information number 1 and genetic information number 2. You can draw them on a 2-dimensional space. And based on this drawing, you want to find out some line that is separating one to the other. So if you apply this idea, you can do lots of interesting things. So where regression, y is continuous. So you can predict any kind of continuous value in your problem setting. So imagine you want to profile each company in terms of debt and equity value and earnings and future product orders. Based on this information, you want to predict future stock price. This is something feasible. Well, based on the size of houses, well, you can try to predict the price of the houses. And if you do so, you may be able to find some pattern that is summarized as a line. So this is a regression line. And similarly, you can think of number of clicks for advertisement. And that may represent the total sales. If you have more clicks, well, you may increase sales. Well, that's the whole idea of all those commercials. And maybe between them, you have this kind of pattern summarized as a single line. So all of these are examples of regression. Where classification is making decision in choosing one of many, choosing one of two, choosing one of three, and so on. So one of the famous problem is identifying the number based on their visual shape. So all these are handwritten digits, and maybe you can represent in terms of the data using this sharp or space. So number 3 can be represented something similar to this. And based on these visual input or textualized input, you want to make a prediction. So well, this is representing 3. Well, first, this is very easy, but well, you can also train your computer program to make that decision. Well, eventually, we want to change all these visual input into bit patterns. And based on the bit pattern, we may be able to make right prediction. Well, oh, this is 3, this is 7, and so on. So, well, this is some examples of classification. And the idea is being developed over years. So, identifying spam mail out of all those regular mail, well, the technology has been complete like early 2000. So in the middle, there is a classifier, and this classifier is reading your emails before you. And if the mail content sounds more like spam, it goes into the spam folder. Other than that, well, you can read them. Well, this is another toy example. So based on the weight and texture, you can identify which of those fruits are orange, or which of those fruits are apple. Well, this kind of thing sounds cheesy, but well, still, well, we can make computers to make decisions like this. Well, that is something amazing. So we talked about supervised learning, and in supervised learning, one class of the problem is classification. Another class of problem is regression. Moving on to unsupervised learning. Here, data is given from 1 to n, and each data given in a singular form. So compared to the previous slide, your data was coming in pair. So you have input X, and you have an associated output Y. And the task was running the relationship between them. That was supervised learning. In unsupervised learning, you are only given the input pattern of the data, and you don't have any target output. Given that, you want to find some interesting pattern, or you want to summarize the data, and so on. So again, we want to discuss two representative problems. One is density estimation, the other is clustering. So density estimation is looking at the data distribution and well, somehow quantize the distribution of the data. So say, well, this is your data. Where you want to sort of model or sort of draw the distribution of the data. So where this is a sort of crowd area, then you have larger bar. Where this is well, sort of less crowded, then you have smaller bar. So where this is a sort of graphical representation of your data distribution, or where we can say this is a density of your data areas. So obviously, depending on the actual appearance of the data, your distribution shape is changing. So based on your data, your density estimation is changing like this dashed line. And moving on to another example of unsupervised learning. So that is something called as clustering. So clustering is grouping data. Well, say you have given this bunch of data, maybe they could be represented as a color and shape. Well, based on those appearance, we can make a couple of several groups of those shapes. So we have green ellipsoid or circles, and blue square, and yellow triangle, and gray hexagons, and so on. So for us, making those groups are easy, but sometimes we have 10,000 of data points where grouping them manually is extremely difficult. So we want to automate them. Also, at the same time, we want to make the computer program to group those data automatically. So that is what machine learning is providing. So we talked about supervised learning, and we also talked about unsupervised learning. And let's moving on to reinforcement learning. So where we simply briefly touch the basis of each of these ideas. Reinforcement learning does not have well clear input and output. Instead, you have an environment and you have an agent. So this agent is playing around in the environment, and each time this agent is taking an action. And based on the changes in the environment, or sometimes you have an explicit evaluator that is called as a critic. So you're basically taking an action and looking at the environment and evaluate your previous action. So within this kind of a framework, you want to run the program for the agent automatically based on the changes in the environment, or based on the interactions between agent and environment. Here is an interesting example for reinforcement learning. So this is a famous example actually, something called as a cart pole. So there is a cart, and there is a pole. And here the goal is to make this pole not falling. So what you can do is making this cart to move to the right or left. And objective is, again, you don't want to let the pole fall over. And well, you want to hold it as long as you can. So well, here comes a evaluation, on the other word, reward. So if you make this pole steady longer, you will gain more reward. So that's basic idea and basic setting. And basically, you are interacting by changing this action and looking at the environment, and evaluating comes to the reward. Based on all those three components, you want to learn how to move this cart, how to control this cart. So this is sort of the result. So at the initial stage, initial episode, where all those cards are goofing around it, so they are not making any intelligent action. But as the episode goes up, well, it is showing some kind of improvement. So it holds the pole for a while, but it goes to one direction eventually. So it is improving, not perfect, but it is improving. And later on, it learned well how to hold the pole still. So it is moving back and forth. And somehow there is some kind of a continuous vibration, but well, it can hold the pole much longer. And later on, the pole is well, much steady, and your control is more well, sophisticated. So well, how to move, how to control this cart is, in this case, learned automatically from the interaction between agent and the environment. So that's the basic idea of reinforcement learning. And using this simple idea, people came up with a bunch of interesting examples. So based on the visual shape and moving the bar here, right or left, well, the mind learned how to play this game. And well, this guy is learning how to go over those bars. So if you go to OpenAI, OpenGym or something, well, you can actually watch the video. They are improving. And well, these are well, just an interesting example at first sight, but these can be more useful in real life. So the same idea is forming the main controller of an autonomous vehicle or those industrial robot arms. So they are actually doing something useful.